So the next thing we're going to talk about is the ideal gas law. The ideal gas law is an energy equation, but it's kind of hidden. We never talk about it as simply an energy equation. So here's my ideal gas law. Pressure times volume is equal to nRT, where n is particles, r is Rydberg's constant, and T is temperature. Why is this an energy equation? Well, it turns out that pressure is force divided by area. Okay? And volume is height, width, which is an area. Oh, I want to go length times an area. For there is a reason for that, nRT. So force times the distance is nothing more than energy, and then the areas cancel each other out. So you end up getting joules. You end up getting work or energy equals nRT. Okay? So that's why it's an energy equation. So when you look at PV equals nRT, you're actually looking at the idea of energy inside of a system can increase the temperature of that system. Once again, yet another relationship between temperature and energy. Now, if we were to say, well, I'm going to increase the pressure of this, or increase or decrease the volume, or anything like that, where it has an effect on my temperature, we can take that temperature idea and say, well, we know temperature, okay, and we can solve that temperature for the average change in kinetic energy. We've already talked about that using this relationship of, for diatomic gases, 3 kT equals average kinetic energy. Okay. So there's some really cool relationships when you talk about the ideal gas law. You can quickly take this idea, this nRT, solving for T, plugging it into here, solving for the average kinetic energy of the particle, and then from the average kinetic energy you can solve for the average velocity per particle. I mean, so ideal is a nice way of floating around. You know, it's a nice little tool there. Now, the thing about ideal gas laws is that the gas has to be ideal. Well, what does that mean? Well, first of all, what it means is that there's no interaction between any other particles inside the gas. They're not gravitationally attracted, they're not electrostatically attracted. There's no attraction trying to consolidate those particles. Okay, so there's no energy of interaction between particles, molecules, or atoms for that. It doesn't really matter either one, which is important, but it's also what we use to define what a gas is. That there's no energy, no potential energy between those particles. So that you know, thing that makes it ideal is not that big of a deal. The other thing that we have to consider when we're talking about ideal gas laws is that when collisions do occur inside there, when an atom collides with another atom, that they're elastic collisions. Now, if you remember, elastic means that energy is conserved. Nothing is wasted. Nothing is converted into into heat or temperature, or deformation or sound, for that matter. Well, yeah, that's not a very hard thing to believe either, because we know that heat is a kinetic energy. It's a molecular kinetic energy. It's motional energy. So the molecule themselves don't heat up. They don't gain temperature. They gain kinetic energy. And that temperature is an expression of that kinetic energy. So that one's not that hard to believe either. And how many of you have ever heard of a deforming molecule? You have a collision and then all of a sudden it's not this. It's a little bit skewed. It's got a bump in it now. So that it's not a hard thing to imagine. Okay, so, and the last thing is that well, there's a couple other things. One more thing is that motion is random. Gases in general have random motion. You don't have bulk movement of particles in one direction or bulk movement of particles in another direction. It can be done, but very difficult to do, because you know it's worse than herding cats. And then the last thing is that it's all elastic collisions with the container. Those particles are bouncing off the container walls. Okay, so that's what makes it an ideal gas. If I forgot anything, please let me know and I'll add it. I mean, it's all really really, I mean, it is important, but it's not really all that important for what we want to use it for. So PV equals nRT. So this is an energy equation. I kind of called it work, and I shouldn't have called it work, because there is a situation in which work isn't being done with this PV equals nRT. Now remember what work is. Work is this force times distance, but I have to have it, or not force times distance, catching myself, force times displacement. So I need to have a displacement in order for there to be work. If I increase the pressure inside of a chamber, I'm putting energy into the system. I'm effectively increasing the temperature of the system, which in turn is effectively increasing the kinetic energy of the system, but it's not necessarily doing work. Okay, and what we mean by doing work, the gas is not doing work on the container. It's not doing work, pushing something. So it's not really doing work. So in order for work to be done in the case of ideal gas, is that you have to have a change in the volume. That's work. It's not that energy is not being put into it, but if you put energy into it, you ignite a gas or something like that underneath it. You begin heating it up, and you increase the pressure. You're not really accomplishing anything. But if you heat up that gas, you're increasing the pressure, and then you release some sort of piston that's associated with that chamber, and that piston rises. You can see how that's work. We're getting work out of that system. So you got this gas in there, then all of a sudden it pushes a piston up. I can use that piston to do all sorts of things for me. It'll do work for me. It will move my car. It will generate electricity. It will do a whole bunch of things. So we have to have that change in the volume in order for work to happen. So when we talk about heat engines and stuff like that, we need to have a change in volume. I mean, think about it the other way. If I add heat to the system, I'm certainly adding energy to the system, but I'm not doing any work. So in order for me to do work in the system, I want to take that piston and then push it down. That way I'm doing the work on the system. I'm decreasing the volume. I have to put work in. Okay? So when we talk about it, this PV equals nRT, PV is energy. Change in V is work. Okay? So if the volume's changing, then we're experiencing work. If there's no change in volume and only a change in pressure, that's not work. Okay?